Hi, everybody. Welcome back to class. We'll be starting in just a couple minutes, so thanks for being here again, as usual. Good morning. Hey, Eva. Good morning. Just another minute and we'll be all ready to go. Okay, guys. Well, welcome back. Good morning, everybody. Good to see you. Drew, I saw your email from earlier. Were you thrown off because of the daylight savings factor? Maybe you were thinking that nobody's here in class, what's going on, but it's because you're operating on the other clock. Perhaps. That was my theory anyway, because I knew there was no issues with the setting up of the meeting. Okay, yeah, so that made sense. Okay, good. Well, welcome back, everybody. Thanks a lot for being here today and attending the meeting. As I had messaged you guys over the weekend, the midterms have been graded, and everybody who sent me a message asking for their score, I've delivered them a response. But if you still want your score and you haven't yet received it, please email me, and I'll send you back your grade with written comments so you'll know exactly how you did on that midterm test. But the class keeps moving on. We're still working now through this topic of metaphysics of time. And let me just jump right in. When we were here last time, who could tell me where we did end? I'm kind of just trying to remember the precise point in my notes. We talked about the twins paradox. We talked about the light clock. Did we get to start talking a little bit about Ted Sider and the concept of analyzing how it is that time moves? Just let me know about that really fast if you could. I'd appreciate it. go back in your memory and tell me what we finished with in this Ted Sider article, because there's a little more from it that I want to pick up on. And if you could just simply refer me to the last point in the notes that we discussed. So, did I show you guys this graph with the train? Yeah? Okay, so I showed you this train graph. Let me then bring you back up to speed on what we were doing there. Okay, good. Thanks, Drew. And thanks, Jason. Okay, so right now, we're still breaking down the article by this philosopher, Ted Sider, American philosopher born in the 60s, still alive. The article in our book is called Time, and it's from 2005. Okay, so in his paper, he starts off by just saying that the concept of time is something that we usually don't think too much about because we just take it kind of for granted. It seems to be something that, we live our lives according to the clock, and we're all familiar with time as a measurement of what we're doing. But when you ask yourself, well, what is time? And you start analyzing it in depth, it becomes very mysterious and weird, because the thing is that it's hard to capture or analyze what it means to say that time moves. People, when we talk about time, everyday people, just common sense talk, we say time flies, time is passing, time's moving quick. No, it's moving slow, it's marching on, et cetera, et cetera. So there's this kind of metaphor built up in our language that time moves. But he says, what exactly can we say about the idea that time moves? What does it really mean to say that time is moving? The problem with that, trying to give an analysis or definition of how time moves, the reason that's difficult to do is because to even define the concept of motion itself, like through space, physical motion, you have to make a mention of time. Like, so I was trying to show you guys that by means of, first of all, just a visual demonstration using my body. Like if I move my hand from this part of the panel to over here, the way that it moves, the explanation of what it means that it is moving is that it's changing its position over time. So it's in different places at different times. That's what it means to move from point A to point B. So if time moves, plugging it into that definition, it would have to imply that time moves by being at different places at different times. But now we're using time as a way to define the movement of itself, and that's circular. I tried to show you guys a graph. In the graph, there were 4 destinations that a train travels through from its origin in Boston to its final destination in Washington. And the graph just showed that it proceeds from the first point to the final point by being in different places at the different times along its journey. So at time 1, it's in Boston. At time 2, it's in New York. At time 3, it's in Philadelphia. At time 4, it's in Washington. Now, if we say that time moves by somehow the present moment moving, I showed you guys that graph too, right? I showed you a graph that involves discussion of the present moment being at one point noon, at a subsequent point 3 p.m., at a further on point in the day 6 p.m., and then 9 p.m., correct? This graph is also included in the notes that we were talking about. Or did we merely talk about the train example? What do you know about that, Drew, or anybody else here that was able to indicate to me where notes ended? The graph about moving through points in time, I think that if I'm looking at your comment and interpreting it right, that we did talk about this second example. So let me just show the graph again, and then we'll just sort of continue from there. So what does it mean to say that time moves? Does it mean the present moment is moving? Maybe, but if so, this kind of graph suggests itself to us. Okay, so like, okay, so maybe we say the present moment moving is what is indicated or intended by the concept that time moves. Right now, okay, yeah, so just it's a recap then, but thank you guys for that. Right now the present moment is 9:06, but it won't stay at 9:06. Like earlier this morning, it was 8 a.m. or something that was the present moment, and relative to then, this was in the future. And later on today, like at noon or around lunchtime, that'll be the present moment, and then this will be in the past. So the present moment keeps on changing. Is this the idea that is expressed when one says that time moves? It seems like it's a noble attempt to try and explain it, but well, he says still though there's a problem, because to draw the graph and to show that the present moment is moving, we have to show how it's at different points in the clock at different times in the time sequence. So we have these 4 time coordinates on the left axis of the graph, but now there's a new question. If the present moment is cycling with respect to these 4 time points, then how are these 4 coordinates assigned in the order 1, 2, 3, and 4? What gives them this linear ordering? That could only make sense if these are further placed within a broader graph in which we have another 3rd order set of time indicators to organize these time coordinates. And that would lead to an infinite regress, which, as you guys have learned in studies on philosophy of religion, infinite regress is thought of as usually something that is absurd or impossible. So what's the better approach then? He says the better approach is to simply abandon this entire concept of time that says that it moves. Let us just reject the idea that time moves, that it has any state of motion, and instead embrace the theoretical implications of Einstein's space-time theory. With Einstein's theory of space-time, we're now able to just disregard the whole concept that time moves, because according to that theory, it doesn't move. All the moments exist. There's one giant set of facts that are all equally real, inclusive of the past, present, and future. None of them is more or less real than any other. And once we accept this conceptualization of space and time, then this entire difficult problem goes away, because there's no problem to be explained if we just deny that time moves in the first place. Then you don't have to say, well, what does it mean that time moves? Because you're just flat out claiming that's not the case, that it does not move. So the space-time theory may be useful because it helps us get rid of the metaphor of time like as a moving thing, like as a flowing river. And here's what he says about that on page 460. Sorry, I meant to say page 459. He said, time's motion has us all tangled up in knots. Maybe the problem is with that idea itself. According to some philosophers and scientists, our ordinary concept of time as a flowing river is hopelessly confused and must be replaced with the space-time theory, according to which time is like space. Okay? So for me now, I need to basically try and show you guys on this board how we are supposed to think then about objects and even ourselves according to this space-time theory of Einstein. Okay, so that requires the drawing of what's called a space-time diagram. And so yeah, let me just draw you a little space-time diagram here. It's the same kind of diagram that you see in figure 4 and in figure 6 in the textbook, but I'm mostly looking at figure 4 here. Okay, so we draw a graph which has these 2 axes and then this horizontal axis running through. So let's say this is the y-axis, this is the x-axis, and this horizontal line represents the time dimension, so that's t. Okay, so now in a space-time diagram like this, objects exist by being placed both in the spatial coordinates of the diagram, but also in the temporal coordinates of the diagram. So say that at this point on the time axis, it stands for the year 2002. Okay, and then over here is 2020. Actually, let me change these numbers just a little bit. I'm trying to make it 2002 because a lot of you guys were born like around that time. It's 2020 now. I know a lot of you are freshmen, and around 18 is when you're going to be in college, freshman year. So let's suppose that this graph is going to display the existence of a human being like you, okay? So you're born in 2002, and let's just say that you have a very nice, long, healthy, happy life, and you live until 2102, so like 100 years old. Okay, now in this graph, let me extend out the letter T a little bit here. So we just show your existence in the following way. Okay, so now, along the horizontal axis, let me ask you some questions about what you see on this graph. Why does the human stick figure that I show inside of the space-time diagram, why does it have less vertical extension on the x-axis back at the beginning point of 2002 on the time axis? Why is it that it's smaller at this point, the little human figure, and slightly bigger as we slide to the right along the t-axis? What do you think that size differential is meant to express? Maybe I can make it a little more pronounced. So what do you think is the reason that it's a small human figurine? Okay, so that is to represent, yes, growth physically. Because obviously if you look back at your original photos of yourself, like from a baby and a toddler, and just your earlier years, you had less mass, you had less volume spatially than you do now. So that signifies growth along the spatial axis, right? So it's a small little baby growing up, becoming older, physically maturing, getting larger, until the timeline cuts at the time where the individual ceases to exist, dies. Here's another question. Why do you think that the streak extends to the right along the horizontal axis? So now I'm not asking why there's more or less vertical height along the x-axis at the beginning, but now why is there this horizontal extension? What is that supposed to show? Well, Eva, let me make sure you're correct on what you understand with your question. The people being born take up space, but not as much as when they're older. I mean, that's clear, right? Because you're bigger physically than you are when you're a baby. So that's shown here in the graph by this being a small human figure, and gradually as time passes, growing and being older. But Dhruv, no, it's not space. The horizontal t-axis is clearly a metric of what? Time, right, Anthony? So we endure through time. We occupy space, we take up some region of space, like whatever chair that you're sitting in right now, you occupy the space seated in that chair. And you occlude, meaning that you crowd out the space for other objects to be in the same position that you're in. But you also have duration across time, not just extension in space, but duration through time. So since you live for some amount of time, however long that you exist is depicted on the graph by having a more or less lengthy horizontal extension along the t-axis. So I mean, if there was like a tragic, child who died or something at 10 years old, being born in 2002, then they would have less extension along the t-axis because there'd only be 10 years of time, as opposed to, in this case, we're showing a 100-year lifespan. If there were things like, antimatter particles that are basically just almost instantaneously annihilated once they erupt into the universe, so they're only there for an instant, then they would just be one time slice along the graph, like one individual dimensionless point along the t-axis. So the longer that the career or existence of the object endures, then the longer this streak would be on the graph that depicts the object. Okay, now, ordinary objects in space-time diagrams have got both three-dimensional spatial dimensions and a fourth temporal dimension. So this is why this is sometimes called four-dimensionalism. These space-time diagrams show the spatial dimensions and this horizontal time dimension. Now, to be fair, I have limitations as I'm working with a two-dimensional board surface. If this was a perfectly detailed graph, then it would have to be rendered in 3 dimensions with like a pop-up cardboard cutout, so that you would see the height dimension, the horizontal dimension, and then the depth. So there would be 3 spatial dimensions plus the temporal dimension running through. So you basically have to imagine that this skewed-looking angled Y line is really just our familiar horizontal axis. And this is the vertical axis through which the intersection point of the t-axis runs. Okay, so now on this 4-dimensional view of objects, and just one more time to be clear, the objects stretch horizontally on the graph because we take up time, and they stretch through the other dimensions because we occupy some amount of space. So on this 4-dimensional view of objects, objects like us and like everything else, tables, chairs, markers, automobiles, planets, every object in the universe has got both spatial and temporal parts, okay? Now, spatial parts of an object are just like the physical, I would say body parts, but in some cases you might not think of inanimate objects having body parts, but you know, like the different, like a table, there's the legs of the table, there's the top of the table. So there are like sections and parts of any object. With regard to you, your spatial parts could reasonably be just called body parts, like, you know, your fingers, toes, torso, legs, arms, head, hands. So you have got spatial parts. Look at them. They're right there in front of you, okay, wherever you're at physically. But in the space-time theory of Einstein that Sider is trying to explain and elaborate on here and defend, you've also got what are called temporal parts. So now I really have to hope you understand that. What is a temporal part? Okay. So a temporal part of an object is just an object at a single moment of time. Okay. All right, so like take one exact moment of time, and the object at that moment, that's one of its temporal parts, okay? And then like for the next subsequent moment in time, that's another one of the temporal parts, and so on and so forth. So let's see. I know we're just getting familiar with this new concept, so it might just take a few moments to really reason through it, but let's try. Based on what I'm telling you here, what you see on this diagram, how many temporal parts of you do you think of you? How many of your temporal parts are shown in like a photo that you take of yourself and you post on social media or something? If you have a pic, right, a picture of you, how many temporal parts of you are displayed inside the picture? That's a question. So now you got to tell me. Taking pictures, we all take pictures. Good, Cameron, it's one. Now, why is it that that's the right answer? That is the right answer. But why is it that a photo of you, a still photo, just shows one temporal part? Correct, it's one. Now I'm just asking us to expand, open that up a little bit. Why, though, is that the right answer, that it's only one? Since you seem to know that it's one. Because it's the person at one moment, exactly, at that very moment. A still photo doesn't capture any time passing. It's recording the light that's taken in by the shutter of the camera at an instant of time, right? Now, if there's a video, say you take a video of yourself, right? You won't be able to give me a number, but like in general, how many temporal parts of you are shown in a video? There are just as many of those temporal parts of you in the video as there are what in the video. So, I mean, a video could be of varying length, but for example, if there's a video of you of any length, then it has to have how many temporal parts, sort of according to a formula? Well, it would certainly be more than one, right, Drew? But more precisely, there would be as many of the temporal parts of you recorded in the video, shown in the video, as there are what in the video? There'd be one for each what? One temporal part of you for each. I know it's hard to determine the exact number, so I'm not asking you for that, like if you said 100. But yes, correct, Megan. There would be just as many temporal parts of you in the video as there are as there are moments. Now, Christopher, you say the number of frames, but keep in mind, right, that the frame rate or the shutter speed of a camera is something that's based on technological limitations. But metaphysically, there are moments that are more infinitesimal than even the most powerful camera could capture. You know, so like if you had 1 billion frames per second, does that capture every moment that occurred within the 1 second? It seems almost impossible to get to the least unit of time. But at any rate, physicists do believe there is a least unit of time. It's called the Planck length. It's sort of the temporal corollary to the smallest physical size, which is believed to exist in physics. At any rate, there's a lot of these temporal parts of you. Even in a short video, there would be, you know, one for each moment. So you say number of frames, Christopher. Think of this as like if it was God's camera. So it was like the perfect camera, and it would capture one image of you for every possible moment that exists within an interval of time. One is almost tempted to say there's infinite number of these temporal parts, but that cannot be, because in that case there would be an infinite number of events occurring even within the smallest interval of time, and then it would be somewhat absurd to suppose that we could fit all those events into any small interval of time, because there'd be no limit to them. So it's anyway a very large but finite number of temporal parts of you are shown in the video. And I just kind of want to keep working this question over so that it really sinks in, so that you understand it, because it's pretty heady, right? Let me ask a new question. How many temporal parts of you are seated right now in whatever chair you're sitting on, or couch, or whatever? Like, how many temporal parts of you are there right now in your chair? At the moment that I ask the question, that is. How many temporal parts of you are now hearing this question? One, right? Because it's a single moment. But how about right now? Is this temporal part that I'm going to ask you about at this point, is it the same one as I just asked you about previously a second ago? So what about the temporal part of you sitting in your chair at this point in time? Is it identical to, or is it different from the other one? Correct, Megan, it's a different temporal part. Why is it that you have a different temporal part sitting in your chair now versus the one that I mentioned about 30 seconds ago? Why are they different? I mean, you're the same person. So how come these are different temporal parts? There's a clear answer, just you can tell me. The reason that these two different moments are two different temporal parts is because it's a new moment in time. Yes, it's a new moment in time. So for each new moment, new temporal part exists in this time sequence of you. And so your whole existence in this space-time universe, according to Einstein, is because you occupy both space and time. Space you occupy by having the familiar physical spatial parts, right? That has shape, that has mass, those are your body parts, and like if you get a haircut, you lose some of those, but then some of them come back. Those are spatial parts. But you also have got what they call temporal parts according to this theory, and the temporal parts are just you at each moment of time. And so you endure through time, and you occupy time by having temporal parts, and you occupy space by having spatial parts. It's just an instant, right, Drew? It's just whatever would be considered the least unit of time measurement. So, I mean, when we use clocks, we're in the habit of like counting off by seconds, right? There's 60 seconds in a minute. But as you guys know, a second is in a way an arbitrary interval. You could have had half seconds and then say we're measuring time in half seconds and there's 120 of them in a minute. Or you could have had a quarter-second interval and said that that's the unit of time. And instead there are 240 of them in a given minute. So what we invent labels for, and the demarcation of each unit is kind of somewhat conventional. But metaphysically, aside from time measurement devices, the idea is that time, of course, has moments within it, and to each one, an object has an individual and distinct temporal part. Okay, so on this four-dimensional view of objects, we have both spatial and temporal parts. A temporal part, as seen on this graph, it's kind of like a slice through the space-time worm, which shows the career of the object. So like if we had a vertical slice, just a cross-section through, that one moment in time, that like still frame, freeze frame of their life, that would be one temporal part. Now, a temporal part of an object is spatially the same size as the whole object is. So like, take a pic of yourself right now, that's one temporal part of you that shows up in the picture, and the temporal part shown in the picture is the same physical size as your whole body. But it's not the same temporal size of you, because the entire aggregation of all your temporal parts forms the object that you actually are. So here's another interesting question to kind of continue on this theme. According to the space-time theory, then, are you fully present right now in your seat or as you're watching this lecture? Are you the person, the whole person, watching this lecture right now? Are you fully present seated in your chair or on your couch? Are you 100% there? That's a yes or no for you. And you can just tell me what you think the right answer would be according to the theory. According to the space-time theory, are you fully present in a single moment of time? Okay, Cameron and Anthony, you're saying yes. Drew, you're saying no. Okay, so are we guessing? What's the reasons for any of these different answers? Why? Okay, Eva, why is it that you're fully present then, according to this theory? If that's what you think, why? Are you fully present? You say yes. I ask you, why are you saying yes? You could say yes, but you can't tell me why. Why? Because you're not stuck in a past moment. Well, there's a misunderstanding, I think, coming out of what you're writing there, Cameron. So the correct answer, I'll just tell you, is no, you're not fully present right now. Because, let's get to it. What is present in your chair right now? According to this theory, not the whole thing that you are. But at each single moment, how much of you is there? In a given moment, like say 9:28 a.m. at exactly like 9:28:02, it's just one of the temporal parts of you. Right, exactly. So you're not fully present there. What's present, what's watching this lecture, is like one of your temporal parts at a time. Now, what is the full thing? What is the complete object that you are? It's the set of all the temporal parts taken across the times that you exist. So what you are in total is the set of all the temporal parts. In other words, all the moments that comprise your life, today, tomorrow, and in the past, present, and future, all those temporal parts of you taken as a whole, taken as a unit, all of them added together, summed up. The summation of all your temporal parts is you. But Eva and Anthony, Cameron, can we understand this point, right, that the summation of your temporal parts is not what's watching this lecture. What's watching this lecture is some of the points in your timeline, right? Because what's not watching this lecture right now is like you as a 10-year-old or you as a 30-year-old. Those parts of you are at different points in your timeline. So there's this like little section in the overall streak of your existence which views this lecture at this morning. But that's not the full object. The full object is the grand total summation of all the parts as taken together. Okay, so you're never fully present in any given moment. Yes, 100%, that's what is being said. You're not. You never get to see the full object because you'd have to exist in a way where you could observe time in multiple times all at once. Like, so you'd have to be trans-temporal. You'd have to somehow be able to view the summation of all time points. But for whatever reason, the brain, human consciousness, this is very mysterious according to this physical theory, but for whatever reason, our consciousness shows us one moment in the time sequence at a time. And also, it goes in a linear ordering, as you guys know, right? Your consciousness proceeds from past, present to future, and then that just becomes the weird thing to try and explain, because according to this theory, there's some kind of illusion there. I've heard people, argue or even speculate that if you were able to witness and observe all the moments of your life all at once, it would be overwhelming and confusing. Like, there's these weird YouTube videos that sometimes people create where it's like every episode of Garfield played simultaneously, and you hit play and you just see like this crazy series of images superimposed on each other where everything's kind of happening at once, all the different dialogues are happening all at once. And it's just a mess because your brain can't sort through it. It lacks coherence and ordering. So, some people think that maybe the nature of physical reality is that all your temporal parts exist in space-time, but for you to be simultaneously aware of them as though they were all happening simultaneously would be just confusing and incomprehensible. So a linear ordering structures the moments so that your brain can, attend to them in the way that makes sense. But yeah, anyway, just expanding on the concept of the space-time diagrams, let's keep in mind where this all started. Ted Sider said that there's fundamental puzzles and paradoxes involved in trying to explain the ordinary common sense notion of time. Because that ordinary idea of time that you have before you ever study philosophy or physics or anything is that, time is moving, it's passing, it's flying, it's moving somehow, and that's just all we know. But he says, well, it's not so easy to explain what it means to claim that time moves. Because ordinarily we think that time is what is needed to even define motion in the first place. So we run into problems of circularity in trying to define the movement of time. Saying the present moment is moving in time is also not much of a better attempt because it still requires us to define the motion of the present within a time sequence. So the only viable alternative, he thinks, is to just go full Einstein and say, never mind, there's a space-time theory, and if we hold on to that, then we do not say that time moves. We just say that all the moments coexist, the past, present, and future, they're all fully set out, and all the moments are equally real. Then we have to entertain the conceptualization provided by these space-time diagrams, that objects like me and you and just anything exist by being located in space at different spatial points, and also by having temporal parts that are set out in a sequence. And those are the moments at which you exist, each one a different temporal part. Okay, so in this case, time doesn't flow, it doesn't move, it just sits there like space. And here he says a few other things about it in the book. In contrast to the ordinary conception of moving or flowing time, the space-time theory says that reality consists of a single unified space-time which contains all of the past, present, and future. Time is just one of the dimensions of space-time alongside the three spatial dimensions, just as it appears to be in these graphs. Time does not flow. Time is like space. Okay, so another way then of thinking about the reconception of time and space that the space-time theory advances is to see how time and space, according to this view, are claimed to have similarities with each other. The next thing Ted Sider does is he tries to point out three similarities between space and time according to the space-time theory. So if you're trying to grapple with these ideas, wrestle with the idea of space-time theory, a fundamentally different orientation towards thinking about time and space, then you have to start seeing time as having greater similarities to the concept of space than you have normally thought of before. And so he just wants to present to you what three similarities between time and space are, as according to this theory. Okay. Okay, so three similarities between space and time according to the quote-unquote space-time theory of Einstein. All right, so first of all, he mentions a similarity in terms of reality. Meaning this: objects that are far away in space are just as real as objects that are present in space, and the same goes for time. Okay, so okay, objects that are far away in space are just as real as objects that are present in space, and the same is true of events in time. So now, to explain the point here, let me just go through this little demonstration. So you see this expo marker that's in my hand right here. Can we agree that this is a real object? Like that it's real? That this is not just like an imagination thing or like a hologram or just something fake. This is not technical, editing or special effects. Can we just agree this is a real thing? This is a real object, this marker? You see me writing with it, so it'd be hard for you to disagree. But that's point one. Okay, good. This is a real object. Now, this was a better example to use when there was a physical classroom. So if you want to substitute for the example of a marker, I think I might even have a better case for you. Look at the computer that you're watching this on, okay? Is that real? I would hope we can agree on that. That's I mean, that's a rhetorical question in a way, because I know that there's nothing you can say that you disagree about that. Like your computer that you're watching this on, or your phone, if that's the case. Does that object really exist? Yes. Okay, now I want you to imagine this. Suppose that for whatever reason, someone, maybe, it could be anybody, or for whatever reason, this computer you're watching this on is taken from where you are. So right now it's with you because you're watching it. But suppose that it was removed from you and taken across the border to Canada. Okay, now, I don't know, maybe some of you are watching this in Canada, but let's say it's taken to another country, okay, from where you're at. If that happened, would it still be a real object? The fact that we moved it from point A, where you are now, to point B, some other country, would that make it no longer be a real thing? Or would it still really exist despite the fact that it's been moved away? Yeah, it would still be real, okay? It's kind of like, take a little baby, right? Like the baby sees the mom and dad in front of them, so they know there they are. Now, maybe when the mom and dad leave the room, the baby's like, where are they? Do they still exist? But we're all adults now, right? And so we understand that an object which is right up in front of you in your face, spatially, you know it's real. But it continues to be real as it moves away from you in space. It's not like the objects exist within a force field of your perception, and then once you can't see them, they stop existing, right? So like the object is just as real as when it's close to you as when it's far away. So if I took this computer and I took it to the next country over, it would still be real. How about another question? Say that I had the means to do it, and I took your computer and I had it sent into space. And now I sent it on a space shuttle towards the moon. So the space shuttle docks on the moon, and now your computer is on the moon. Now you're on Earth. This computer you're watching this on is on the moon, but does it still exist, and is it still real? I hope we can understand the point of my example here, that yeah, it's still real. No matter if it's just the next state over, no matter if it's in another country, no matter if it's on the moon. And if I could take it in the Voyager spacecraft, send it outside the solar system, and allow it to just keep getting further and further away from you as you stay on the Earth, there's no point where it stops being real, no matter how close, no matter how far it is. So the only point that I'm mentioning here is that how far or close to you in space something is has nothing to do with how real it is in terms of existing. It's just as real when it's close as when it's far, okay? That's space. Now, about time, all this is saying is that time is exactly the same. So events that are not happening present moment, right now, like your birth, or way later on, maybe you having kids, you're getting married, right? Those events that are not present moments, they are just as real as this present moment is. So according to the space-time theory, you're not allowed to say, well, the present moment is the only real moment, because the past is gone, and the future is just totally undefined. According to the space-time theory, it's not just the present moment that's real. It's also the future moments and the past moments, and they're all just equally as real as each other. So just as much as an object taken away from you in space continues to still really exist, events and moments that are far away from you in time are just as real as this present moment is right now. So it's not only the space around you that exists, but it's the space that's far away from you that also exists. And it's not just the time that's presently happening that exists, but it's the time that's in all these other distant points of time that also really exist. Okay, so hopefully that makes sense to you. Sometimes when we talk about the distance away from us in time of a moment, we even employ spatial metaphors. Like we say, hey, remember back then when I was a little kid? Like back is a behind me sort of spatial metaphor. Or we look forward to something. We say, I'm looking forward to the election, like forward as though I'm moving forward in space towards some future event. But despite these metaphors in language that signify movement or distance away from you in the future and past, all the moments are just as real as the present one is, at least according to the space-time theory. So like the dinosaurs way back then, that moment of space-time still exists in this universe. Just as much as this moment does, just as much as the development of the coronavirus vaccine out into the future really exists. And we're not just talking about the potential for it to exist in the future, but the actual events of people taking the vaccine, like in 2021, if it happens, that exists because all the moments are real, not just the present. Okay, so it's very weird, but it's the idea. Now, the second similarity between space and time, according to the theory mentioned by the author, is in terms of parts. Okay, and what he means by that is that just objects take up space by having spatial parts, and they take up time by having temporal parts. Okay, so the second similarity that he's mentioning between time and space here is that in both cases of space and of time, there are parts. Okay, so in space, the parts are just the physical parts. Like on this marker, one part of it is the cap, another part is like the housing of the actual ink cartridge. You know, there's like the bottom half, the top half. And in my case, you've got my hands, my arms, my torso, head, neck. So there are different spatial parts. And the reason that I have mass and that I take up some volume that's in this chair is because of the spatial parts. But in the space-time theory, time also has got parts. And in the case of time, they're temporal parts, an object at a single moment of time. And in the same way that we occupy space by having spatial parts, we occupy time or endure through time by having some number of temporal parts. And again, it's really insisted on in the theory that they're equally as real as each other. So like, look at your left hand. You know it exists. You don't doubt that it exists because there it is. The existence of your left hand, according to this theory, is just as real and factual as the existence of your future temporal parts or of your past temporal parts. It's not like they're just figments of your mind or that they're somehow not actually real. They are real and just as real as the parts of your body. The future and past temporal parts of you are just as real as the current physical parts of your body. Okay, so that's the second similarity between time and space. And then the third and last one that he mentions is in terms of these two interesting words, here and now. So let me go over that with you. Okay, so how are these two terms similar? Well, both terms are relative terms. And so what that means is that the meaning of each of these terms depends on the context of the speaker. Okay, so both are relative terms. Whose meaning depends on the context of the speaker. Okay, so, oh, sorry, missed the word, whose meaning depends on the context of the speaker. So let's quickly go over a little example. This is actually much harder now with the remote learning class setup. But, okay, because like many of us are in different countries and stuff, so this kind of throws the example off a little bit. But suppose that I say here in California, here in California, I shouldn't say in California, let me rephrase that. Out here, Gavin Newsom is the governor. Here, Gavin Newsom is the governor, okay? Now, I'm speaking, and I'm speaking that statement, and it's true. Because when I say here, our governor is Gavin Newsom, where does here refer to when I say that? Where's the location of the place called here? Like, where on the map is here located? If you look on a map, will you see a destination that's labeled with the word here? Well, no, you'll just see the names of different countries. So I'm asking you kind of a trick question, but I still want you to ponder it. What would you answer someone if they asked you, where is here located? Okay, Senna, when I say here, it is California because I'm talking to you from Long Beach, California. So my word here refers to the place where I am when I say it. But say that someone's in New York right now, and they say here, the governor is Andrew Cuomo. Now, when they say the word here, Are they referring to California? The other speaker on the East Coast? When they say out here, the governor is Cuomo. They're not referring to California, but they're using the same word here. So where does here refer to? A minute ago, you said it referred to California, and now you're saying it refers to New York, but this is the point. Then now you can give me some type of answer to this tricky question. It's relative, yes, it's relative. So the reference of the place called here depends on the condition of the speaker who's speaking. So it depends where the speaker is, basically. Here is a relative term. It refers to wherever the speaker is at when they say it. So if I say, here, it's cloudy. It's true, because if I look out my window, here in Long Beach, it's pretty overcast. But there are other parts of the globe right now where the weather's different. And if they say here, it's not cloudy, are we contradicting each other? When I say here it's cloudy and they say here it isn't? No, it's because the one word here can relatively refer to two different locations when two different speakers are using it. So now with the words now, it's exactly the same. So when is the moment now? At what time is now happening? Now is just yeah, well, relative, it's fine. Relatives, you could say subjective, but I think it's a good point to notice the distinction. It's better to say relative. But with the term now, it's very similar, right? If I were to ask you what time is designated by using the word now, like now we're learning this material, what time of day or date is the word now in reference to when I just said here? Well, it would refer in this case to like 9:48 a.m. on November the 2nd. But people who were taking a lecture on, time in the 50s, when they say, okay, is everyone ready now to open your books? Were they referring to 2020? No, they were referring to the date and time of whatever year that was back in the 50s, because when they said now back then, now referred to the time at which they were speaking. So now refers to whatever time the speaker is speaking at. Here refers to whatever place the speaker is positioned at. So they're both relative terms, and there's no like objective existence of the place called here or the time called now. Now is just whenever someone says it. So there's no single present moment. In 100 years from now, in 2120, when people are studying like the coronavirus pandemic and the early years of the 21st century, they'll be like, now let's study some history. And they won't be referring to now 2020, but 2120, because that's the time then they'll be speaking in. So it's another important insight into the similarities of time and space to see that they're just both relative terms. That disabuses us of the common idea that the present moment is privileged and special, that there's no other moment that is now, and it's only just right now. According to this conception of time and space, now is relative to every moment. If a speaker speaks the word now at that moment, then that's now relative to the context of that speech act. Okay, so we've pretty much now wrapped up the rest of the TED Cider. When we do come back next time, we're going to just cap off, or at least try to start capping off some of our discussions about time by looking at one last author on this subject, and that's David Lewis and the Paradoxes of Time Travel. It's a very fun and kind of weird article, so we'll get into it. I also sent a video over the weekend. Check it out if you have a chance. That'll help you in getting clear about the work of Einstein and this relativity stuff. The final paper prompt, which I'm going to assign within the next week, one of the topics is that's optional. There's 3 optional topics, but one of the options is to report on the space-time and metaphysics of time. Another one will be epistemology, and then another possible option will be philosophy of mind, which we'll kind of start talking about next week. But all right, guys, I guess I'll let you guys go. Have a good day. If you get to participate in the election tomorrow, that'd be awesome too. I know it's a civic duty for a lot of us to feel like voting is important. But anyways, then I'll let you guys go for now. Have a great day. Continue to message me if you want any scores. Cameron, I saw you here. I'm going to get to your message right after class. I was just a little bit caught up, but I will do that in a short moment. So I have to teach till 11, but after that. Okay, so thanks, everybody. Take care. Bye-bye.